Welcome back to Nocturnal Notions. Tonight, there's nowhere to go and nothing to follow. Imagine the night sky, not as something distant, but as something vast and patient. Above you, the solar system moves, slowly, quietly, without effort. Planets continue along their paths, the same paths they've followed for billions of years. No sudden turns. No urgency. Just motion, so steady, it feels like stillness. As you settle in, picture wide, open space, where distance softens thought and time stretches until it no longer feels important. Light drifts across the darkness, taking minutes, sometimes hours, just to arrive. Nothing here is in a hurry. Tonight, we'll explore 50 gentle facts about the solar system, not to memorize, not to analyze, but simply to notice. You don't need to stay awake for any of it. Let each fact pass, like a quiet star, sliding across the edge of awareness. Allow the calm rhythm of space to slow your breathing, to loosen your thoughts, and to carry you, comfortably, toward sleep. We begin with our sun, that brilliant star at the center of everything we know. When we look up at the daytime sky, we see just one glowing orb among countless stars in the universe. But this particular star, our sun, holds an almost unimaginable dominance over our corner of space. The sun contains 99.86% of all the mass in our entire solar system. Think about that for a moment. All the planets, all the moons, all the asteroids and comets and dust, everything that orbits our star, all of it combined makes up less than 1/7 of 1% of the solar system's total mass. The sun is truly the master of its domain, its immense gravity holding everything in place, keeping Earth in its comfortable orbit, season after season, year after year. Without this gravitational anchor, our planet would simply drift away into the cosmic void. But the sun holds us here, safely, steadily, as it has for billions of years. Let's travel now to Mars, that rust-red world that has captured human imagination for centuries. If you could stand on the Martian surface and look out across its ancient landscape, you might encounter one of the most staggering geological features in our solar system. Valles Marineris, the Mariner Valley, stretches across Mars for 4,000 kilometers. To give you a sense of scale, imagine a canyon system that would span nearly the entire width of the United States. The Grand Canyon, magnificent as it is, extends only about 446 kilometers. Valles Marineris is almost 9 times longer. In some places, this Martian canyon plunges 7 kilometers deep into the planet's crust. Scientists believe it formed billions of years ago as the planet's crust stretched and cracked, possibly influenced by the volcanic bulge of the massive Tharsis region nearby. It's a scar on Mars, a window into the planet's ancient past, lying there silently beneath the thin pink sky. Now let's drift even further from home, beyond the planets, beyond the realm where the sun's influence feels strong, to the very edge of what we call our solar system. Out there, 2 small spacecraft continue their lonely journey. Voyager 1 and Voyager 2, launched in the 1970s, have traveled farther than any human-made objects in history. They crossed what we call the heliopause, that invisible boundary where the solar wind from our sun finally yields to the interstellar medium, the space between the stars. Voyager 1 crossed this threshold in 2012. Voyager 2 followed in 2018. And even now, decades after leaving Earth, these remarkable machines continue to send back faint signals, whispers from beyond our solar neighborhood, traveling for hours across space at the speed of light before reaching our radio telescopes. Inside each Voyager is a golden record, a message from humanity to any beings who might someday find these travelers, containing sounds and images from Earth, a greeting from our small blue world to the universe beyond. Let's return now to the inner solar system, to Venus, Earth's so-called sister planet. Venus and Earth are similar in size, and they orbit relatively close to one another. But Venus is a world of extremes and mysteries. One of its strangest qualities is the way it spins. While most planets in our solar system rotate counterclockwise when viewed from above their north poles, Venus rotates clockwise. This is called retrograde rotation. Scientists aren't entirely certain why Venus spins this way. Perhaps a massive collision in the distant past knocked it into this unusual orientation. But here's what makes it even more peculiar. Venus rotates so slowly that one complete rotation takes longer than one trip around the Sun. A single Venusian day, the time from one sunrise to the next, lasts about 243 Earth days. But a Venusian year, one orbit around the Sun, takes only about 225 Earth days. So on Venus, a day is actually longer than a year. Imagine watching the Sun crawl across that thick, yellowish sky, taking months to make its journey from horizon to horizon, before finally, slowly, setting. Our Sun is so vast that its scale almost defies comprehension. We've already mentioned that it contains nearly all the mass in our solar system. But let's think about its volume for a moment. If the Sun were hollow, if you could somehow open it up like a container, you could fit 1 million Earths inside. 1 million. Imagine each grain of sand on a beach representing our entire planet, our oceans, our mountains, our cities, and you'd need 1 million of those grains to fill the Sun's volume. And yet, despite this enormous size, the Sun is actually just a medium-sized star, what astronomers classify as a yellow dwarf. There are stars out there hundreds of times larger. But for us, orbiting at just the right distance, our Sun is perfect, neither too large nor too small, providing just the right amount of warmth and light for life to flourish on Earth. Let's return once more to the innermost planet, Mercury, that small, cratered world racing around the Sun. Mercury is a planet of contradictions. During its day, surface temperatures can soar to 800 degrees Fahrenheit, hot enough to melt lead. The Sun appears more than twice as large in Mercury's sky as it does from Earth, blazing down with intense radiation. And yet, in permanently shadowed craters at Mercury's poles, where sunlight never, ever reaches, scientists have discovered water ice. Water ice on the hottest planet in the solar system. These polar craters act like cold traps, preserving ice that may have arrived via comet impacts billions of years ago. In the eternal darkness of these deep craters, temperatures plunge to as low as -370 degrees Fahrenheit. Light and dark, heat and cold, existing side by side on this small, swift world. Everything in our solar system, the Sun, the planets, the moons, the asteroids, all of it began from the same cosmic event. 4.6 billion years ago, in a relatively unremarkable region of our galaxy, there existed a vast molecular cloud. This cloud contained hydrogen, helium, and trace amounts of heavier elements forged in stars that had lived and died before our Sun was born. Something, perhaps a nearby supernova explosion, disturbed this cloud, causing it to begin collapsing under its own gravity. As it collapsed, it spun faster, flattening into a disk. At the center, material accumulated and heated up until nuclear fusion ignited, and our Sun was born. In the disk around this newborn star, particles of dust and ice began sticking together, slowly growing larger, forming pebbles, then boulders, then planetesimals, and finally planets. 4.5 billion years is a time span difficult for the human mind to grasp. But if you compress the entire history of the solar system into a single year, humans would have appeared only in the last few minutes before midnight on December 31st. Now we travel to Jupiter, the giant of our solar system, a world so massive that all the other planets could fit inside it. Jupiter has dozens of moons, each a world unto itself. One of these moons, Io, is perhaps the most geologically active body in the entire solar system. Io is caught in a gravitational tug-of-war between Jupiter and its neighboring moons, Europa and Ganymede. This constant pulling and squeezing generates tremendous internal heat, keeping Io's interior molten. As a result, Io hosts over 400 active volcanoes. Imagine a world in constant eruption, plumes of sulfur and sulfur dioxide shooting hundreds of kilometers into space, lava flows painting the surface in yellows, reds, oranges, and blacks. Astronomers have nicknamed Io the pizza moon because its colorful, mottled surface resembles a pizza. It's a violent, beautiful moon, a reminder that worlds in our solar system are not static, but dynamic and ever-changing. Here on Earth, we often think of the stars as fixed and unchanging. We navigate by them, tell stories about their patterns, and watch them wheel overhead night after night. The North Star, Polaris, has guided travelers for centuries, sitting almost motionless in the northern sky while other stars appear to rotate around it. But even this is not permanent. Earth's axis, the invisible line around which our planet spins, doesn't point in exactly the same direction forever. Instead, it traces a slow, gentle wobble, like a spinning top winding down. This wobble, called axial precession, takes approximately 26,000 years to complete one full cycle. Right now, Earth's North Pole points toward Polaris. But thousands of years ago, it pointed toward a different star, Thuban, in the constellation Draco. And thousands of years from now, it will point elsewhere again, perhaps toward Vega. The sky above us is not fixed. It's part of a cosmic dance that unfolds over timescales far longer than human lifetimes, a patient, endless rhythm. Finally, let's drift out to Saturn, that magnificent ringed world. Saturn's rings are one of the most recognizable sights in our solar system. When Galileo first observed them through his primitive telescope in 1610, he couldn't quite make out what they were. He thought perhaps Saturn had ears or handles. Only later did astronomers realize these were rings, vast, flat structures encircling the planet. The rings are made primarily of water ice, countless chunks ranging from tiny grains to pieces the size of houses, all orbiting Saturn in an impossibly thin disk. If you could somehow stand on the rings, though they are far too insubstantial to support your weight, you'd be surrounded by a shimmering field of ice, extending tens of thousands of kilometers in all directions, yet less than a kilometer thick in most places. The rings may have formed from a moon that wandered too close to Saturn and was torn apart by tidal forces, or perhaps from remnants of the solar system's formation that never coalesced into a moon. They won't last forever. Slowly, gradually, material from the rings is falling into Saturn's atmosphere, a rain of ice that may cause the rings to disappear entirely in another 100 million years or so. But for now, they remain a beautiful crown on the solar system's second-largest planet. In the summer of 2025, astronomers detected something extraordinary passing through the constellation Sagittarius. A visitor, not from our solar system, but from the vast spaces between the stars. This interstellar traveler was designated 3I Atlas, the third confirmed object from beyond our solar system ever observed. The first, Oumuamua, arrived in 2017, a mysterious, elongated object tumbling through space. The second, Borisov, came in 2019, clearly a comet with a glowing tail. Now 3i Atlas has joined this exclusive group of cosmic wanderers. Imagine the journey this comet has taken, born perhaps around a distant star we'll never see, ejected from its home system through some gravitational dance, drifting through the galaxy for millions, perhaps billions of years, and then, just by chance, passing through our little corner of space. For a brief moment, we could observe it, track its path, analyze its composition, before it continued onward, back into the endless dark between stars. These interstellar visitors remind us that we're not isolated. Our solar system is part of a much larger story, and sometimes, rarely, we get glimpses of the greater universe wandering through our neighborhood. Jupiter, the giant, the king of planets. We've already mentioned its dominance, but let's truly appreciate its scale. Over 1,000 Earths could fit inside Jupiter's volume. 1,000 complete copies of our world, our oceans, our continents, our atmosphere, all tucked inside this enormous ball of gas. Jupiter is so massive that its gravity influences the entire outer solar system. Some scientists even wonder if Jupiter helped protect Earth in our early history by deflecting dangerous asteroids and comets inward or flinging them away entirely. When you look at Jupiter through even a small telescope, you can see its cloud bands, stripes of white, brown, and red stretching across its face, storms larger than our planet swirling through its atmosphere. The Great Red Spot, a storm that has raged for at least 300 years, is slowly shrinking, but still remains large enough to swallow Earth whole. Jupiter spins faster than any other planet. One complete rotation takes just under 10 hours. This rapid spin creates powerful winds and helps drive the planet's complex, ever-changing weather patterns. A giant world, churning, spinning, dominating the outer solar system. Far, far from the Sun lies Pluto, that small, cold world that once held the title of ninth planet, though now it's classified as a dwarf planet. Pluto is so distant that sunlight takes over 5 hours to reach it, and when it arrives, it's so faint that noon on Pluto would look more like deep twilight on Earth. Despite the cold, temperatures dropping to nearly -400 degrees Fahrenheit. Pluto has an atmosphere. It's incredibly thin, far more tenuous than Earth's, made mostly of nitrogen with traces of methane and carbon monoxide. But here's what makes it fascinating. Pluto's atmosphere changes with its seasons. Pluto's orbit is highly elliptical, meaning sometimes it's closer to the Sun and sometimes much farther away. When Pluto approaches the Sun during its 248-year orbit, some of its surface ice warms just enough to sublimate, turning directly from solid to gas, and this creates a temporary atmosphere. But as Pluto moves away from the Sun again, cooling down, that atmosphere gradually freezes and falls back to the surface as snow. Nitrogen snow, drifting down through the dim light, accumulating on Pluto's icy plains and mountains. A distant world breathing in and out over centuries, exhaling atmosphere when warmed, inhaling it again when the deep cold returns. Our solar system exists inside a protective bubble. The Sun constantly emits a stream of charged particles, the solar wind, flowing outward in all directions at incredible speeds. This wind creates what we call the heliosphere, a vast magnetic bubble that surrounds our entire solar system. The heliosphere extends far beyond the planets, past Neptune, past Pluto, out to where it finally meets the interstellar medium. And this bubble serves a crucial purpose. The galaxy is filled with cosmic rays, high-energy particles accelerated by supernovae, pulsars, and other violent cosmic events. These cosmic rays stream through space at nearly the speed of light. But the heliosphere shields us from about 90% of these galactic cosmic rays. Without this protection, Earth's atmosphere would face much higher radiation levels, potentially making life's emergence far more difficult. We live inside this invisible shield, the sun's influence protecting us. Even as we venture to the edge of the solar system, we're still wrapped in the sun's embrace. Let's return to Mercury once more, that swift little world closest to the sun. Mercury races around the sun faster than any other planet, completing one orbit in just 88 Earth days. That's its year. But here's the strange part. Mercury's rotation, its day, lasts 59 Earth days. So on Mercury, you'd experience only 1.5 days in a single year. The reason for this odd relationship involves tidal locking effects from the sun's gravity. Mercury spins 3 times for every 2 orbits it makes. This creates bizarre effects for any hypothetical observer on Mercury's surface. If you could stand at certain locations on Mercury and watch the sunrise, you'd see the sun rise partway above the horizon, then reverse direction and set again, before finally rising once more and beginning its long journey across the sky. Time moves strangely on Mercury, where days are longer than years, and the sun performs celestial loops in the black sky. Now let's travel to the outer reaches again, to Neptune, that deep blue world of ice and storms. Neptune has 14 known moons, but the largest by far is Triton. Triton is unusual for many reasons. First, it orbits Neptune backward, in a retrograde direction, opposite to the planet's rotation. This suggests Triton didn't form alongside Neptune but was instead captured, perhaps plucked from the Kuiper belt in the ancient past when the solar system was young and chaotic. Second, despite being one of the coldest places in the solar system, with surface temperatures around -390 degrees Fahrenheit, Triton is geologically active. The Voyager 2 spacecraft detected active geysers on Triton's surface, plumes of nitrogen ice and gas erupting through the frozen crust, shooting up to 8 kilometers high before falling back down in the weak gravity. These geysers suggest internal heat sources, perhaps tidal heating from Neptune's gravity, or perhaps radioactive decay in Triton's core. A captured moon, orbiting backward, erupting ice into the void. Triton is a strange and wonderful world at the edge of our planetary family. We often think of the solar system as static, planets in fixed orbits around an unmoving sunday. But the sun itself is moving. Our entire solar system, sun, planets, moons, and all, is orbiting the center of the Milky Way galaxy. We're located about 26,000 light-years from the galactic center, in one of the spiral arms, and we're traveling through space at approximately 515,000 miles per hour. Even at this tremendous speed, our solar system takes about 230 million years to complete one orbit around the galaxy. Think about that. The last time our solar system was in this same position in the galaxy, dinosaurs had not yet evolved on Earth. Earth was in its Triassic period, a world dominated by early reptiles and primitive forests. Since then, we've traveled all the way around the galaxy and returned. When our solar system completes its next orbit, 230 million years from now, what will Earth look like? Will humanity still exist? Will new species have evolved? The galaxy turns slowly, patiently, and we ride along, a small mote of dust and light in the great cosmic wheel. Saturn has many moons, over 80 have been discovered so far, but one of the strangest is Iapetus. From a distance, Iapetus looks like it was painted 2 different colors. One hemisphere is as dark as coal, covered in material so black it reflects less than 5% of the sunlight that hits it. The other hemisphere is bright, almost white, made of relatively clean water ice. Scientists believe the dark material may be debris from other moons, gradually coating one side of Iapetus as it orbits Saturn. But that's not the only strange thing about this moon. Iapetus has a ridge running along its equator, a mountain range that circles nearly the entire moon, rising about 20 kilometers above the surrounding terrain. Imagine a walnut, with its characteristic seam running around its middle. That's what Iapetus looks like. No one knows exactly how this ridge formed. Perhaps Iapetus spun much faster in the ancient past, and the ridge is frozen evidence of that rapid rotation. Or perhaps it's the remnant of a ring system that collapsed onto the moon's surface billions of years ago. Iapetus hangs in space, half light, half dark, girdled by an unexplained mountain range, a cosmic mystery waiting to be solved. When we think of the hottest planet in our solar system, we might assume it's Mercury. After all, it's closest to the Sun. But we'd be wrong. Venus holds that distinction. Venus is the hottest planet, with surface temperatures reaching around 900 degrees Fahrenheit, hot enough to melt lead. The reason for this extreme heat is Venus's atmosphere. While Mercury has almost no atmosphere to trap heat, Venus has an incredibly thick atmosphere, over 90 times the pressure of Earth's at sea level. This atmosphere is made mostly of carbon dioxide, a powerful greenhouse gas. Thick clouds of sulfuric acid reflect much of the sun's light back into space, which is why Venus appears so bright in our sky. But the heat that does make it through the clouds gets trapped by all that carbon dioxide, creating a runaway greenhouse effect. The heat builds and builds, unable to escape back into space. As a result, Venus is hotter than Mercury despite being nearly twice as far from the Sun. It's a world of crushing pressure and blistering heat, a cautionary tale written in the sky about what can happen when a planet's atmosphere goes wrong. Finally, let's return home, to Earth, and to our moon. That bright companion that lights our nights and drives our tides. The moon wasn't always where it is now. When it first formed, likely from debris created when a Mars-sized object collided with the early Earth over 4 billion years ago, the moon was much, much closer. Some estimates suggest it was perhaps 15 times closer than it is today, appearing enormous in the sky. But the moon has been slowly drifting away from us ever since. The same tidal forces that cause the moon to raise bulges in Earth's oceans also transfer energy and angular momentum, gradually pushing the moon into a higher, more distant orbit. Right now, the moon is moving away from Earth at about 1.5 inches per year, roughly 3.8 centimeters. That might not sound like much, but over millions of years, it adds up. Millions of years ago, days were shorter because Earth spun faster, and the moon loomed larger in the sky. Millions of years from now, if humans are still here to see it, days will be longer, and the moon will appear smaller. Solar eclipses, those spectacular moments when the moon passes perfectly in front of the sun, are only possible because the moon appears almost exactly the same size as the sun in our sky. But this is temporary. Eventually, the moon will be too far away, too small in appearance, to completely cover the sun. We live in a special time, when the cosmic alignment is just right for total solar eclipses to occur. The moon continues its slow retreat, like a boat pulling away from shore, still connected to us by invisible tidal ropes, but gradually, inevitably, drifting into deeper space. Let's drift further outward now, beyond the familiar planets, to the distant frontier of our solar system. Close your eyes and imagine traveling past Neptune, out into the cold and quiet reaches of space where sunlight grows faint and the darkness deepens. Beyond Neptune lies a vast region called the Kuiper Belt. This is a ring, a disk really, of icy bodies stretching billions of miles across. Think of it as the solar system's attic, a collection of ancient remnants from the formation of the planets, frozen in time and space. These objects are made mostly of ice, water ice, methane ice, ammonia ice, mixed with rock and dust. Pluto resides here, orbiting among countless smaller cousins. Tens of thousands of these icy bodies drift in the Kuiper Belt, and scientists estimate there may be hundreds of thousands more we haven't discovered yet. Some are tiny, barely larger than mountains. Others, like Pluto, are massive enough to be spherical, pulled into round shapes by their own gravity. The Kuiper Belt extends from about 30 astronomical units from the Sun, where Neptune orbits, out to perhaps 50 astronomical units or more. An astronomical unit is the distance from Earth to the Sun, about 93 million miles. So we're talking about a region that begins nearly 3 billion miles from home. Out there, the Sun looks like just a very bright star, no longer a blazing disk but a point of light in the darkness. The Kuiper Belt marks one boundary of our solar system, though even beyond it lies the scattered disk and eventually the Oort cloud, an even more distant shell of comets. But the Kuiper Belt is where the planets end and the true frontier begins. Let's return inward now, back to Mars, that rusty world we visited before. We mentioned Valles Marineris, the enormous canyon. But Mars has another claim to fame in the record books of our solar system. On Mars stands Olympus Mons, the largest volcano in the entire solar system. This shield volcano rises nearly 14 miles above the surrounding plains, that's about 22 kilometers. To put this in perspective, Mount Everest, Earth's tallest mountain, reaches about 5.5 miles high. Olympus Mons is almost 3 times taller. Its base is so wide, about 374 miles across, that it's roughly the size of the entire state of Arizona. If you could stand on the Martian surface at the base of Olympus Mons and look up, you wouldn't even be able to see the summit. It would be beyond the horizon, hidden by the curve of the mountain itself. The volcano's slopes are gentle. Shield volcanoes form from flowing lava rather than explosive eruptions, so climbing it would be more like a very, very long walk uphill rather than a technical climb. Olympus Mons is likely extinct now, though scientists can't be entirely certain. Mars has no plate tectonics like Earth, so volcanic hotspots can build up in one place for billions of years, creating these enormous mountains. Olympus Mons is a monument to Mars's volcanic past, standing silent and cold under the pink sky. For a long time, astronomers thought that only giant planets like Saturn and Jupiter could have ring systems. But in recent years, we've discovered something surprising. Some asteroids, small rocky bodies typically found in the asteroid belt between Mars and Jupiter, also have rings. Chariklo, for instance, is a Centaur asteroid, about 250 kilometers across, and it has 2 narrow rings orbiting it. Another object, Quaoar, in the Kuiper Belt, also appears to have a ring. These rings are faint, delicate things, nothing like Saturn's magnificent bands, but their very existence challenges what we thought we knew about how rings form and persist. Rings around giant planets make sense. The planets are massive enough to capture and hold debris from destroyed moons or passing comets. But asteroids? They are so small, with such weak gravity, that holding onto a ring seems nearly impossible. The particles should either fall onto the asteroid or drift away into space. Yet somehow, these rings exist, clinging to their tiny parent bodies, adding another layer of mystery to our understanding of the solar system. At the center of our solar system burns the sun. We see its light, we feel its warmth, but what's happening inside that blazing sphere? The sun's core, hidden beneath hundreds of thousands of miles of roiling plasma, reaches temperatures of about 27 million degrees Fahrenheit. At these extreme temperatures and pressures, hydrogen atoms are forced together so violently that they fuse, combining to form helium. This nuclear fusion releases enormous amounts of energy. Every second, every single second, the sun fuses about 620 million metric tons of hydrogen into helium. That's more than 600 million tons every second. The energy released by this process works its way outward through the sun's layers, taking thousands of years to travel from the core to the surface, before finally radiating out into space as the sunlight that warms our world. The sun has been doing this for 4.5 billion years, and it will continue for another 5 billion years or so before it exhausts its hydrogen fuel. Right now, in this moment, the sun is in its prime, stable, steady, reliable, fusing hydrogen, generating heat and light, making life possible on Earth. Let's journey now to Uranus, that strange blue-green world tilted on its side. Most planets in our solar system have a relatively small axial tilt. Earth tilts about 23.5 degrees, which gives us our seasons. But Uranus tilts 98 degrees. It's essentially rolling around the sun like a ball rather than spinning like a top. This extreme tilt means Uranus has the most extreme seasons in the solar system. During a Uranian summer, one pole points almost directly at the sun and experiences continuous daylight for over 20 years, while the other pole endures over 20 years of continuous darkness and frigid cold. Then, as Uranus continues its 84-year orbit around the sun, the seasons shift. The pole that was in light gradually tilts away, and the one that was dark slowly turns toward the sun. The transition periods, spring and fall, are when both hemispheres receive some sunlight, though even then, the distribution is wildly uneven. Scientists aren't entirely sure why Uranus tilts so dramatically. The most popular theory suggests a massive collision early in the solar system's history knocked Uranus onto its side. Whatever the cause, Uranus now spins through space in its own peculiar way, a world of extremes, where seasons last longer than many human lifetimes. In 2014, the European Space Agency's Rosetta spacecraft achieved something remarkable. After a 10-year journey through space, Rosetta rendezvoused with a comet called 67P Churyumov-Gerasimenko. The spacecraft actually went into orbit around this comet, a rubber duck-shaped object about 4 kilometers long, and deployed a small lander called Philae to touch down on its surface. For months, Rosetta studied the comet up close, watching as it approached the sun and began to warm up, releasing gas and dust to form a glowing coma and tail. Scientists analyzed the composition of these gases, and they discovered something unpleasant. If you could somehow smell Comet 67P, it would reek of rotten eggs, cat urine, and bitter almonds. The rotten egg smell comes from hydrogen sulfide. The cat urine odor is from ammonia. Other compounds detected include formaldehyde and methanol. This noxious mixture tells us about the comet's composition, what ices and organic compounds were present in the early solar system, frozen into these ancient bodies. Comets are often called dirty snowballs, mixtures of ice and rock that formed billions of years ago. By studying them, we're essentially smelling the primordial solar system, and apparently, it didn't smell very good. There's a pattern to the way things move in our solar system. If you could float above the sun's north pole and look down, you'd see nearly everything orbiting in the same direction, counterclockwise. The planets orbit this way. Most moons orbit their planets this way. Even the Sun itself rotates counterclockwise. This isn't a coincidence. It's a remnant of how the solar system formed. Remember that collapsing molecular cloud we mentioned earlier? As it collapsed, it was already rotating slowly, just a gentle spin acquired from the motions of gas clouds in the galaxy. But as the cloud collapsed and shrank, conservation of angular momentum caused it to spin faster and faster, just like a figure skater spins faster when they pull their arms in. This spinning cloud flattened into a disk, and that disk was rotating counterclockwise when viewed from what would become the solar system's north pole. When planets formed from this disk, they inherited its rotation direction. So nearly everything in our solar system orbits the same way, moving along in the same cosmic dance, tracing paths laid down 4.5 billion years ago when the solar system was born. We've mentioned Jupiter's Great Red Spot before, but let's linger on it for a moment. This is not just any storm. It's a high-pressure anticyclonic storm, an enormous vortex of clouds and winds that has been raging continuously for at least 350 years, and possibly much longer. When astronomers first observed Jupiter with telescopes in the 1600s, they saw the spot and noted it in their records. It's been there ever since, swirling in Jupiter's southern hemisphere. At its largest, the Great Red Spot was 3 times wider than Earth, big enough to swallow our entire planet with room to spare. In recent decades, the spot has been shrinking. Scientists aren't sure why. Today it's roughly 1.3 times Earth's diameter, still massive, but smaller than it once was. Winds at the edge of the storm can reach speeds of over 400 miles per hour. The storm's red color likely comes from complex organic molecules in Jupiter's atmosphere, though the exact chemistry is still debated. Imagine a storm larger than our world, with winds that would tear apart any structure humans could build, raging for centuries without end. Jupiter is a world of extremes, and the Great Red Spot is its most famous feature. Uranus is often called an ice giant, along with Neptune. But don't let the name fool you. You couldn't land on Uranus. There's no solid surface to stand on. If you somehow survived the journey to Uranus and tried to descend through its atmosphere, you'd pass through layers of hydrogen and helium gas. Then gradually the atmosphere would become denser and denser, transitioning to a hot, slushy mixture of water, methane, and ammonia ices. But there's no clear boundary where the atmosphere ends and something solid begins. The pressure and temperature would increase gradually as you descended, and the materials around you would transition from gas to liquid to strange, exotic forms of matter crushed by immense pressure. Deep in Uranus's interior, there might be a small rocky core, but you'd never reach it. Long before then, you'd be crushed by pressures millions of times greater than Earth's atmosphere. Uranus is a world without a surface, a giant ball of gas and ice in various states, all blended together, all the way down. And now, let's consider the richness of our solar system's family. Over 200 moons orbit planets and dwarf planets throughout the solar system. Jupiter alone has over 90 confirmed moons. Saturn has 83. Even Mars, tiny by comparison, has 2 small moons, Phobos and Deimos. Each moon is a world unto itself. Some are dead, cratered rocks. Others, like Jupiter's Europa or Saturn's Enceladus, have liquid water oceans beneath their icy shells and might even harbor life. Some moons have atmospheres. Some have volcanoes. Some are captured asteroids, while others formed alongside their planets. Ganymede, Jupiter's largest moon, is bigger than the planet Mercury. Titan, Saturn's largest moon, has lakes and rivers on its surface, though they are filled with liquid methane and ethane rather than water. 200 worlds, each with its own story, orbiting through the solar system, held by gravity to their parent planets, reflecting sunlight in the darkness. We live in a solar system that's far more diverse and complex than we ever imagined. At the outer reaches of our solar system, where sunlight is barely more than starlight, astronomers search for hidden worlds. In 2025, after 7 years of careful observation, astronomers confirmed the existence of an object designated 2017 OF201. This object is remarkable not just for what it is, likely a dwarf planet cousin to Pluto, but for where it is. It orbits far beyond Neptune, in the most distant reaches of the trans-Neptunian region. Finding such objects requires patience and sophisticated techniques. Astronomers use advanced algorithms to scan through millions of images, looking for faint points of light that move ever so slightly against the background stars. These distant objects move slowly, taking hundreds of years to complete a single orbit around the Sun. So detecting their motion requires comparing images taken months or even years apart. 2017 OF201 is one of these elusive wanderers, a frozen world drifting through the outer darkness, only now revealing itself to our searching telescopes. Each discovery like this reminds us that the solar system's edge is not empty, not a sharp boundary, but a gradually thinning population of ancient, icy bodies, each with its own story to tell. Let's journey now to Uranus and visit one of its strangest moons. Miranda is a small moon, only about 300 miles across, but when Voyager 2 flew past in 1986 and captured close-up images, scientists were stunned by what they saw. Miranda's surface is a chaotic patchwork of different terrains jumbled together. There are regions of parallel ridges and grooves. There are massive cliffs, some over 3 miles high, taller than any cliff in our solar system when compared to the size of the body they are on. There are cratered plains next to bizarre coronae, large oval features that look like racetrack ovals carved into the ice. The whole moon looks like it was assembled from mismatched pieces. The most popular explanation is that Miranda suffered a catastrophic collision early in its history, an impact so violent it nearly shattered the moon completely. The fragments then slowly reaccumulated under their own gravity, coming back together in this jumbled, chaotic arrangement. Imagine being torn apart and reassembled, pieces fitting back together but not quite matching how they were before. That's Miranda, a moon that bears the scars of ancient violence, frozen in place, orbiting Uranus in the cold and quiet dark. In February of 2025, NASA's Perseverance rover was exploring Jezero crater on Mars when it encountered a rock unlike any seen before. The rock, informally named Cheava Falls, contained peculiar spotted patterns, small white and black spots that reminded scientists of leopard spots. But these weren't just interesting patterns. When Perseverance analyzed the rock with its sophisticated instruments, it found organic molecules, carbon-based compounds that are the building blocks of life as we know it. The spotted patterns themselves could have been formed by chemical reactions that on Earth are often associated with microbial life. The white spots might represent chemical energy gradients that microbes could have exploited. The black spots contain iron and phosphate, materials that could have supported ancient life. Scientists are being careful, very careful, not to claim definitive proof of life. These features could also have been created by non-biological processes. But this discovery represents the strongest evidence yet that Mars might once have hosted microbial life in its ancient past, when Jezero crater held a lake of liquid water billions of years ago. Perseverance has collected a sample of this rock, and someday, perhaps in the 2030s, a future mission will bring these samples back to Earth, where scientists can study them in detail and perhaps finally answer the question, did life ever exist on Mars? We've spoken before of the Voyager spacecraft, those intrepid explorers launched in the 1970s. Let's appreciate once more what they've accomplished. Voyager 1 and Voyager 2 are the only human-made objects to leave the solar system and enter interstellar space. Voyager 1 crossed the heliopause in August of 2012. Voyager 2 followed in November of 2018. These spacecraft are now traveling through a realm no human-built machine has ever explored, the space between stars. Out there, beyond the sun's protective bubble, cosmic rays are more intense. The solar wind no longer dominates. The spacecraft are encountering the true interstellar medium, the stuff that fills the spaces between star systems. Even now, more than 45 years after launch, both Voyagers continue to function, though their power is fading as their plutonium generators decay. Within the next few years, they'll run out of power and fall silent. But they'll continue coasting through space for millennia, eventually passing near other stars tens of thousands of years from now, carrying their golden records, messages from Earth to the cosmos. Beyond Neptune, in the Kuiper Belt, orbits one of the strangest objects in our solar system. Haumea is a dwarf planet, roughly the same size as Pluto, but shaped nothing like it. While most large objects in space are roughly spherical, pulled into round shapes by their own gravity, Haumea is elongated, shaped like a potato or a rugby ball. The reason for this bizarre shape is rotation. Haumea spins faster than any other known large object in the solar system, completing one rotation every 4 hours. That's incredibly fast for something roughly 1,000 miles across. This rapid spin creates centrifugal force that stretches Haumea outward at its equator. As a result, Haumea's equatorial diameter is about 50% wider than its polar diameter. Imagine a spinning blob of clay, flattening and stretching as it whirls. That's Haumea. Scientists believe Haumea spins so fast because of a massive collision billions of years ago, an impact that not only set it spinning but also blasted off fragments that now orbit nearby as small moons and smaller objects. Haumea is a world literally shaped by violence and motion, still spinning frantically after billions of years. The discovery of 2017 OF201 in 2025 was made possible by a new generation of powerful telescopes designed to survey the entire sky repeatedly. One of the most important of these is the Vera C. Rubin Observatory in Chile. This remarkable facility achieved first light in the summer of 2025, the moment when its enormous camera captured its first images of the night sky. The Rubin Observatory is designed to photograph the entire visible sky every few nights, creating an ever-updating map of the heavens. Its camera is the largest digital camera ever built for astronomy, taking images with billions of pixels. This allows astronomers to detect incredibly faint objects and track how they move over time. Objects like 2017 OF201 that lurk at the solar system's edge, barely visible even in powerful telescopes. The Rubin Observatory is challenging our ideas about the outer solar system, revealing that the region beyond the Kuiper Belt is not empty, but populated with distant, icy worlds we're only just beginning to discover. Each new detection pushes the known boundary of our solar system a little farther out into the dark. Let's turn our gaze now beyond our solar system entirely to the stars themselves. Barnard's star is one of our nearest stellar neighbors, just 6 light-years away. It's a small, dim red dwarf star, much smaller and cooler than our Sun. For decades, astronomers have searched for planets around Barnard's star, and in 2025, they announced success. 4 small exoplanets orbit this nearby star. One of them is particularly intriguing. It's only about 1/5 the mass of Earth, making it one of the smallest exoplanets ever detected. These planets orbit close to their star, completing their years in just days or weeks. Because Barnard's star is so cool, even planets orbiting this close might have temperate climates. We don't yet know if any of these worlds are habitable, but the discovery is exciting nonetheless. Barnard's star is so close that future telescopes, perhaps large space-based observatories in the coming decades, might actually be able to study these planets' atmospheres, searching for signs of life. We're finding worlds around our nearest neighbors. Perhaps someday we'll find life there too. The search for planets beyond our solar system has accelerated dramatically in recent years. By late 2025, NASA's tally of confirmed exoplanets, planets orbiting other stars, surpassed 6,000 worlds. 6,000. Each one is a discovery, a confirmation that planets are common throughout the galaxy. Some of these exoplanets are nothing like anything in our solar system. Hot Jupiters orbiting closer to their stars than Mercury orbits the Sun. Super-Earths larger than our planet but smaller than Neptune. Planets orbiting in systems with 2 or even 3 stars. But astronomers are also finding systems that look more like home. Systems with multiple planets in roughly circular orbits, some in the habitable zone where liquid water could exist. The more we search, the more we find. And with new telescopes like the James Webb Space Telescope now studying exoplanet atmospheres, we're beginning to analyze not just whether planets exist, but what they're made of, what their climates are like, and whether they might support life. The universe is full of worlds, more than we ever imagined. Finally, let's visit one more distant dwarf planet. In 2005, astronomers discovered an object in the outer solar system that would change how we think about planets. This object, eventually named Eris, is located in the scattered disk beyond the Kuiper belt. When astronomers measured Eris, they found it was slightly smaller than Pluto in diameter, but here's the crucial part: it's more massive. About 27% more massive, in fact. Eris has a small moon named Dysnomia, and by observing Dysnomia's orbit, scientists could calculate Eris's mass precisely. The discovery of Eris created a crisis in planetary classification. If Eris is larger and more massive than Pluto, and Pluto is a planet, then shouldn't Eris be a planet too? But that would mean accepting many more objects as planets. There are likely dozens or hundreds of Pluto-sized objects in the outer solar system. In 2006, the International Astronomical Union responded by creating a new category, dwarf planets. Pluto, Eris, and several other large objects would be classified as dwarf planets rather than full planets. The decision was controversial and remains debated even today. But it reflects a deeper truth. The solar system is more diverse, more complex, and more populated than the simple list of 9 planets we once learned in school. Eris orbits out there still, along with Pluto and Haumea and many others, dwarf planets in a rich, varied solar system. Venus, that brilliant evening star, that hothouse world wrapped in crushing clouds. We've spoken of Venus before, but there's something remarkable happening high in its atmosphere that defies easy explanation. At the surface, Venus rotates incredibly slowly, taking 243 Earth days to complete one rotation. If you could stand on Venus and watch the thick clouds above, you might expect them to drift slowly, matching the planet's leisurely spin. But instead, the upper atmosphere races around the planet at tremendous speed. Winds at the cloud tops circle the entire planet in just 4 Earth days. 4 days. This means the atmosphere is rotating about 60 times faster than the planet itself. Scientists call this phenomenon superrotation, and it remains one of Venus's great mysteries. What drives these winds? How does the atmosphere maintain such different speeds from the solid planet below? Theories involve complex interactions between solar heating, the thick atmosphere's circulation patterns, and the peculiar way Venus's slow rotation affects atmospheric dynamics. But no one has a complete answer. Venus's atmosphere rushes overhead, a river of sulfuric acid clouds racing around the planet, while far below, the rocky surface turns slowly, almost imperceptibly, beneath that crushing sky. Now let's travel to Neptune, that distant blue world at the edge of the planetary realm. Neptune orbits so far from the Sun that it receives only about 1/900th the sunlight that Earth does. You'd expect such a distant, cold world to be relatively calm, frozen and still. But Neptune is anything but calm. Neptune has the fastest winds in the solar system, reaching speeds up to 1,500 miles per hour. That's nearly twice the speed of sound on Earth. These winds tear through Neptune's atmosphere, creating dark storm systems that appear and disappear over months or years. But here's the puzzle: where does the energy for these winds come from? Neptune receives very little heat from the Sun, yet it radiates about 2.6 times more energy into space than it absorbs from sunlight. Neptune has an internal heat source, perhaps leftover heat from its formation, still slowly leaking out billions of years later, or perhaps heat generated by chemical processes in its interior. This internal heat drives convection in Neptune's atmosphere, creating powerful updrafts and circulation patterns that manifest as those incredible winds. Neptune is a world powered from within, a blue jewel of a planet, far from the Sun, yet burning with internal fire. The Sun, our life-giving star, holds many mysteries despite being the closest star to us. One of the strangest involves temperature. The Sun's visible surface, the photosphere, has a temperature of about 10,000 degrees Fahrenheit. That's extraordinarily hot, hot enough to vaporize any substance we know. But if you could travel upward from the surface, through the thin chromosphere, into the Sun's outer atmosphere called the corona, you'd find something bizarre. The corona is millions of degrees hot, sometimes reaching temperatures of several million degrees Fahrenheit. How can the outer atmosphere be hundreds of times hotter than the surface below? It violates our everyday intuition about heat. Imagine standing near a campfire, and the air 3 feet away from the flames is somehow much hotter than the flames themselves. This is called the coronal heating problem, and astronomers have been puzzling over it for decades. The answer likely involves magnetic fields. The Sun's surface is covered with powerful, twisted magnetic field lines, and these fields extend up into the corona. When these magnetic fields reconnect and snap, they release tremendous energy, heating the surrounding plasma. But the exact mechanisms remain mysterious. The Sun's corona glows with heat we don't fully understand, a reminder that even our closest star keeps secrets. Mercury, that small, scorched world closest to the Sun. Mercury formed 4.5 billion years ago, born from the same disk of material that created all the planets. Like all young planets, Mercury was hot, its interior molten from the heat of formation and radioactive decay. But over billions of years, Mercury has been slowly cooling down. As its massive iron core cools, it contracts, shrinking slightly. And when the interior contracts, the surface has to adjust. Mercury's crust doesn't fold smoothly. Instead, it breaks and buckles, creating long, winding cliffs called scarps. Some of these scarps stretch for hundreds of miles and rise over a mile high, towering cliffs marking where the crust cracked and one section was thrust up and over another. The Messenger spacecraft, which orbited Mercury from 2011 to 2015, mapped thousands of these scarps across Mercury's surface. And here's the remarkable part: Mercury is still contracting. This process hasn't finished. Even now, billions of years after its birth, Mercury is slowly, incrementally shrinking, its interior cooling, its surface cracking and adjusting. Mercury is a living geological world, not in the sense of having life, but in the sense of being active, changing, evolving even today. Let's return once more to Jupiter and its Great Red Spot. We've mentioned this enormous storm before, but let's consider how it's changing. Historical records suggest the Great Red Spot has been visible for at least 350 years, possibly longer. In the 1800s, observers noted the spot was enormous, about 25,000 miles across, large enough to swallow 3 Earths side by side. But the spot has been shrinking. By the late 20th century, it was perhaps 15,000 miles wide. Recent observations show it's now under 10,000 miles across. The spot is shrinking at an accelerating rate. Why? No one knows for certain. Perhaps the storms and atmospheric dynamics that feed the Great Red Spot are changing. Perhaps it's interacting differently with nearby jet streams. Some scientists wonder if the Great Red Spot might eventually disappear entirely, though that could take decades or centuries. For now, the spot remains, smaller than it once was, but still vast, still churning, still that distinctive rusty red color against Jupiter's pale clouds. We're witnessing a change in one of the solar system's most iconic features, watching as something that has endured for centuries slowly transforms before our eyes. Far out at the edge of the solar system lies Pluto, that small, heart-marked world we've visited before. When the New Horizons spacecraft flew past Pluto in 2015, it revealed a world far more active and complex than anyone expected. One of the most surprising discoveries was nitrogen ice, vast plains of frozen nitrogen covering much of Pluto's surface. But this ice isn't static. On Pluto, nitrogen ice behaves somewhat like glacier on Earth. The ice flows, moving slowly across the surface, driven by convection and sublimation. In some regions, nitrogen ice collects in deep basins. The ice at the bottom, under the weight of the ice above, becomes slightly warmer and less dense, causing it to slowly rise while cooler ice sinks, creating convection cells like those in a lava lamp, but moving over thousands of years instead of seconds. In other areas, nitrogen ice sublimates, turning directly from solid to gas in Pluto's thin atmosphere, and then refreezes elsewhere, falling back as snow. These processes sculpt Pluto's surface, creating smooth plains, shallow pits, and strange polygonal patterns. Pluto, despite being so cold and distant, is geologically active, its nitrogen ice flowing and changing, reshaping the landscape in slow motion. Saturn, the ringed jewel of the solar system, has another wonder we haven't yet discussed. At Saturn's North Pole, there's a storm unlike anything seen anywhere else in the solar system. It's a massive hexagon. Yes, a six-sided geometric shape, a hexagon formed by clouds and winds, approximately 20,000 miles across. Each side of the hexagon is wider than Earth's diameter. The hexagon rotates with Saturn's interior, completing one rotation every 10.5 hours. Winds along the hexagon's edges reach about 200 miles per hour. The hexagon has been observed since the Voyager missions in the 1980s, and it's still there, stable and persistent, decades later. How does a hexagonal storm form and maintain itself? The answer involves fluid dynamics and rotating systems. In laboratory experiments, scientists have created hexagonal patterns in rotating fluids under certain conditions. The specific combination of rotation rate, wind speeds, and atmospheric dynamics at Saturn's pole creates a standing wave pattern that locks into this hexagonal shape. But why 6 sides and not 5 or 7? That remains mysterious. Saturn's hexagon is beautiful, a perfect geometric shape carved by wind and motion in the clouds of a giant planet, a reminder that nature can create patterns of startling regularity and elegance. Finally, let's return home to Earth and consider the invisible shields that protect us. High above Earth's surface, trapped within our planet's magnetic field, lie the Van Allen radiation belts. These are regions of space filled with high-energy particles, electrons and protons captured from the solar wind and cosmic rays. Earth's magnetic field prevents these particles from reaching the surface, instead trapping them in 2 main belts, an inner belt about 1,000 to 6,000 miles above Earth, and an outer belt from about 12,000 to 25,000 miles up. These belts are dangerous. Astronauts passing through them receive significantly higher radiation doses. Satellites can be damaged by the intense particle environment. But the Van Allen belts aren't static. During solar storms, when the Sun ejects massive clouds of charged particles toward Earth, the belts can swell dramatically, merging together or spawning temporary third belts. Sometimes they weaken, sometimes they strengthen. The belts breathe and shift in response to the Sun's activity. They are dynamic structures, constantly adjusting to the ebb and flow of solar wind. Earth's magnetic cocoon protects us from this radiation, but the protection itself is changeable, responding to the Sun's moods, expanding and contracting with each solar storm that sweeps past our world. And with that, our journey draws to a gentle close. Let these images rest softly in your mind: the racing winds of Venus, the shrinking red spot, the hexagon at Saturn's pole. All is well. All is peaceful. The cosmos continues its eternal dance, and you can rest now, drifting gently, peacefully, into deep and restful sleep.